and I'm presenting my final year project titled An Investigation into the Use of Artificial Intelligence to Monitor Future Squirrel Populations in Scotland. This project combines machine learning with citizen science data to create predictive models for wildlife conservation. Since the introduction of grey squirrels in the late 19th century, Scotland's native red squirrel population has faced significant decline. Current monitoring methods are either costly and geographically limited, or suffer from data quality issues such as duplication when relying on citizen science contributions. Building on these challenges, 3 research questions have been identified. Firstly, identify and effectively manage duplicate observations in citizen science data, a critical issue affecting data quality. Second, how can machine learning incorporating spatial dependencies generate reliable population predictions across Scotland's diverse regions, extending beyond the limit of localised surveys? And finally, how can interactive visualization tools transform complex ecological data into accessible insights, providing feedback to citizen scientists and encouraging continued participation in wildlife monitoring? A comprehensive approach was developed to address these research questions through a 4-stage methodology that encompasses data sources, pre-processing, modelling components, and user-facing elements. The first stage involved processing the Scottish Squirrel database through a custom duplicate detection algorithm that combines exact coordinate matching with proximity-based detection. The next step involved engineering spatial temporal features, including regional density and previous year counts to capture population dynamics. The predictive model uses random forest regression, which achieved an R-square score of 0.849 with cross-validation during development and 0.79 in the final test set. Finally, the interactive Streamlit dashboard was created, which visualizes both historical data and future predictions with confidence intervals, making complex ecological information accessible to both researchers and citizen scientists. The entire solution is backed by MongoDB for secure and efficient data storage. The development journey followed an iterative process across 6 distinct phases, colour-coded on this timeline. The process started with literature research to establish methodological foundations, followed by the data acquisition and exploratory data analysis of the Scottish Squirrel database. A significant milestone was completing the duplicate detection algorithm in iteration 3, which evolved through multiple trials. Initially, August et al.'s 2020 fixed distance threshold was attempted, but wasn't able to adapt to various GPS accuracies. Success came from a 2-stage solution, combining Goodchild and Lee's 2012 exact coordinate matching with Chapman et al.'s 2020 dynamic threshold concept, which when combined identified 5.63% of records as duplicates, aligning perfectly with Callahan et al.'s 2020 findings on citizen science data quality. During the model development in iteration 4, a challenge was encountered when spatial lag features contributed only 0.5% to prediction accuracy, far less than the 20 to 30% improvement anticipated from Dorman et al.'s research. By adapting and shifting focus to temporal features, which account for over 86% of the model's predictive power, the model was able to give a more accurate score. The final iteration focused on creating an accessible interface for citizen scientists, with design choices informed by user-centered design principles. The application consists of several files. SquirrelRedPy is a source code for the actual application itself. The styles folder is for visual styles for the application. Requirements.txt are the packages needed to be imported into Python to run the application, and the README setup instructions.txt has instructions on how to run the application. So to run the application, first we have to open a command prompt window. We have to change the directory into the current directory and then paste streamlit squirrelred.py. This will launch the application. We can see in the top right the running icon. This is indicating that data is loading and a trade-off to ensure that data processing happens live as opposed to pre-computed results. On the left side of the application you can see the main navigation panel. The sidebar provides access to all 4 main sections of the application: the distribution map, model metrics, temporal reliability, and the about page. Each tab serves a specific purpose. The current distribution view displays the most recent snapshot of red squirrel sightings across Scotland. We can see the interactive heat map visualization where the intensity of colour represents the density of observations. Areas with more intense orange and red indicate higher concentrations of sightings. The statistics show a total of 8,973 sightings distributed across 32 local authorities. The table provides a detailed breakdown by region, with Perth and Kinross having the highest number with 1,836 sightings. This view serves as our baseline against which our predictions and historical comparisons can be evaluated. It's worth noting that these patterns reflect both ecological factors and citizen science reporting patterns, which is why our model incorporates multiple features to account for these influences. In the future predictions view, within the distribution map page, we can explore projected red squirrel populations using the random forest model. The slider at the top allows users to adjust the prediction year from 2020 up to 2025. You'll notice the model is predicting a 14.1% decrease in overall sightings based on historical data. When we move the slider to 2025, this changes to an increase of 1.3%. The choropleth map displays predicted squirrel densities across Scottish local authorities, with darker shades indicating higher predicted populations. The table below provides detailed regional predictions. What's particularly valuable here is the inclusion of upper and lower confidence intervals for each prediction, showing the model's uncertainty. For example, for Dumfries and Galloway, while our prediction is 1,322 sightings, the 95 confidence interval ranges from 1,127 to minus 419. Disclaimers or information for end users are included at the bottom of many pages. The historical comparison view allows users to examine changes in red squirrel sightings between any 2 years from 2011 to 2019. The years start at 2011 due to reporting for earlier years being highly sporadic. In this example, we're comparing 2015 to 2019. The map uses colour coding to show increases and decreases across regions, with red showing increase and blue decreases. The metrics below the map reveal a significant overall increase, from 5,100 sightings for the mixed source database in 2015 to 8,973 in 2019. That's an increase of 3,873 sightings, or about 76%. This substantial growth could indicate either actual population increases or improved citizen science participation. The table provides a region-by-region breakdown of these changes. Perth and Kinross shows the largest absolute increase with 898 additional sightings, while Stirling saw a proportionally large increase, from 403 to 930 sightings. One technical implementation challenge was designing the colour scale to show both positive and negative changes across the regions, while keeping the visualizations accessible to users with colour deficiencies. We can also change the years. For example, here we can compare 2011 to 2017. Now let's explore the Model Performance Metrics page, which details information about our random forest regressions model's performance capabilities. The time series visualization compares the model's predictions against the actual sightings data from 2011 to 2019. The blue line represents actual recorded sightings, while the dashed red line shows what our models predicted for those years. What's impressive here is how closely the predicted values track the actual observations, especially considering the significant rise in squirrel sightings after 2014. You can see that the model captures both the overall trend and many of the year-to-year fluctuations, though there are some minor deviations in specific years. Below the map, we can see 3 performance metrics to quantify the model's accuracy. The first is mean squared error. Of 187,794. This measures the average squared difference between predicted and actual values. While this number seems large, it's important to remember that we're dealing with thousands of squirrel sightings, so squared errors accumulate quickly. The second is root mean squared error of 433. This is the squared root of the mean squared error, given an error measure in the same unit as our observations. With typical annual counts in the thousands, an RMSE of 433 represents good predictive performance. And third, the mean absolute error of 403. This is the average absolute difference between predicted and actual counts, showing that on average, our predictions were off by about 403 sightings. These metrics together demonstrate that our model achieves strong predictive performance, especially considering the variability inherent in mixed source data. The ability to track the significant increase in observations from approximately 3,500 in 2011 to over 8,000 in 2019 is particularly notable, as capturing such dramatic changes is challenging for many predictive models. One of the implementational challenges was ensuring the graph remained clear and interpretable despite showing many years of data. This was addressed through careful colour selection and line styling. The regional performance view of the model metrics takes an exceptionally long time to load, even with caching. This is because of all the complex geospatial calculations and large dataset being processed for each region. As the name suggests, this page analyses how the model performs across different regions of Scotland. The page is divided into two sections: the Regional Statistics Table and the Regional Prediction Accuracy Map. The table represents a detailed breakdown of our model's performance by region. Each row represents a local authority area in Scotland, showing the total number of squirrel sightings recorded, the years of available data, and most importantly, the prediction accuracy of that region. The colour coding makes it easy to identify high-performing regions in green versus those where the model struggles in red and yellow. We can see that the model performs exceptionally well in regions with substantial data, such as Perth and Kinross, with over 9,000 sightings and a 90.3% accuracy rate. South Lanarkshire stands with the highest regional accuracy of 91%, despite having a relatively small sample size and only 56 sightings over 5 years. Regions with lower accuracy rates, like West Dunbartonshire of 41.7% and North Ayrshire with 47.4%, typically have fewer sightings and more erratic reporting patterns, making predictions more challenging. Below the table, we see an interactive choropleth map that geographically visualises these accuracy rates. The map is coloured based on the model performance of each region, allowing users to identify spatial patterns in prediction accuracy. The predominantly red coloration of Scotland indicates strong overall performance across the country. There's also a summary metrics at the bottom of the page. The Temporal Reliability Analysis page provides critical insights into the seasonal and yearly patterns of squirrel sightings across Scotland. At the top, we see the monthly distribution chart, showing clear seasonal patterns in citizen science reporting. April stands out as a peak month with 8,681 sightings, representing 17.7% of all observations. This spring peak likely corresponds to increased squirrel activity and human outdoor presence. We also see secondary peaks in September and October, each accounting for about 10.5% of annual sightings, while December shows the lowest activity with just 1,683 records. Below, we see the yearly trend analysis, visualising the remarkable growth in squirrel sightings from 2010 to 2019. The trend line shows relatively stable numbers between 2011 and 2014, followed by a significant upward trajectory in 2015. The most dramatic increases occurred in 2017 and 2018, with jumps of 23.2% and 39.8% respectively. The year-on-year changes table quantifies these trends precisely. While most years show positive growth, 2013 experienced a 13% decline, and 2016 saw a minor 9.5% decrease. However, the overall trend is strongly positive, with an average annual increase of 13.6%. Finally, we have the About page, which is an informational page about the project. This contains all the information about where the data was sourced from, how it's been processed, such as duplicate removal, spatial analysis, and temporal processing, the analysis methods used for predictive modelling, temporal analysis and regional analysis, technologies used to build the application such as Streamlit, Python, etc., the libraries used. Finally, there are acknowledgements and special thanks to everybody who's made this possible. The Squirrel Red dashboard successfully addresses our core research questions by delivering an accessible, data-driven solution for red squirrel population modelling in Scotland. With the predictive model attaining 72.9% average regional accuracy, effectively identifying and removing 5.63% of potential duplicate records, and creating visualization tools that reveal both spatial distribution patterns and temporal trends, including a significant 13.6% average annual growth in sightings. The system provides conservation managers with previously unavailable insights into population dynamics, seasonal patterns, and regional variations, enabling more targeted and effective conservation strategies and greater citizen science participation. This project demonstrates that AI-enhanced citizen science data can indeed serve as a reliable foundation for wildlife population monitoring and prediction. I'd like to thank you for viewing, and I hope you've enjoyed this as much as I have.